Yeah, right.
Yeah,
Cool.
that's good one.
Do a quick introduction. Yeah, so our final speaker this morning is Dr. An-Chieh from UCSD. He's the PhD student under Professor Xiaolong Wang at the UCSD, and his research focuses on multimodal foundation model for spatial understanding and actional intelligence with applications in embodied AI and robot navigation. He has an internship at NVIDIA and Adobe, also the winner of our Qualcomm Innovation Fellowship. Yeah, very nice. And today his topic is about efficient, sorry, I think, yeah, it's updated. The topic is efficient spatial reasoning and long horizon planning. Yeah, thank you.
Yeah, hi. My name is An-Chieh, and thank you, Shai, for the introduction. And I'm a PhD student at UC San Diego, advised by Xiaolong. And unfortunately, Xiaolong cannot come here today for some reason. So I will be presenting some of our work on grounding 3D reasoning and long horizon actions in vision language models and also action models. Yeah, so I will basically focus on what is currently missing in vision language models and show how we can bridge the gap to build a real robust and long-term robust systems. Yeah, so talking of robust systems. So this brings us to the core premise of generalist robot policies. So ideally, we want robots that can follow open-ended language instructions, and we want the robot to also seamlessly adapt to new environments. And we also want the robot to be able to really complete long horizon tasks, which are really useful for humans, right? And the most important thing is that we want the policy to be a general policy so that we don't really need to do task-specific fine-tuning for like each task. And this dream is becoming more and more possible because of the rapid progress of the large vision language models like Gemini, GPT-4, or open source models like Kun or Llama, Lava. And as you can see from this Gemini 3 sample, these models already possess like really strong visual language understanding and reasoning capabilities, right? So because of this, a lot of recent work, they try to leverage these vision language models as a foundation to build vision language action models. And it's pretty simple. We just connect the vision language model with some action prediction head. And then these systems can now turn language instructions together with the observations into robot behaviors. And this has already led to pretty impressive progress across different tasks, different platforms, and in real world. So for example, for manipulation, now we can see like robots performing real household activities, such as like picking up the plates and then wipe it. And also similarly, we see in navigations, now robots can follow language instructions to move through indoor and outdoor environments. And we're also seeing this success in like full body control, where we see like humanoid robots are now starting to perform pretty complex and behaviors that need to coordinate, like walking and interact with the objects. So right now, a lot of exciting work is focusing on how to scale these VOA models. Like, for example, what is the correct data to use? Some people like focus on how to scale up the teleoperation data. Some say that we need to use egocentric videos, or some say we need to use like UMI style grippers or some sort of like special embodiments. And also some people start studying on like how to preserve the VOM knowledge while like fine-tune the VOA models. And as we push forward with this like training VOA pipeline, it brings out another question that are the current underlying vision language models fully equipped for the physical demands of robots? Like training pipelines are evolving really fast, but if the fundamental vision language models cannot really like have a solid grasp of the world, then the VOA will just inherit the same limitations. So in this talk, I will reveal two bottlenecks in vision language models. and which is first, it is space blind to the sync geometry, and the second is that it is plane blind to the time horizons. And talking of the space blind problem, like here is a video example from the spatial intelligence benchmark called MMSI video. So basically, the model will be asked to find the fastest way out from the yellow tone room. And basically, from the last few frames of the video, we can see that the correct answer is just to go straight, turn right after the bathroom, and then continue straight through the door to exit. But the results from the Gemini 3.1 Pro are just basically wrong, and it would just hallucinate a lot of explanations to justify its wrong answer. So even with super impressive language capabilities, these foundation models are just still cluey on geometry. So here are the quantitative results of this benchmark, which just reflect this exact limitation. So on this benchmark, the gap is over nearly 60 points between the human performance and Gemini 3.1 Pro. So basically, even top performing models nowadays are still deeply space blind, and when we evaluate it on these 3D tasks. And beyond the spatial problem I just mentioned, we also see the bottleneck of the plane blindness problem, over time horizons. So for example, on the left side, it is the robot is trying to perform a manipulation task, opening the right box, close it, and then reopen the left box. So this requires the model to keep track of the task progress to avoid getting stuck in the loop. So you can see from the video here, it just keeps opening the same box because it has no idea of what is the progress. So on the right one is another very similar sample, but it's a counting task or a repetitive task, like wiping a plate a couple of times, like 5 times or three rounds. Okay, yeah. So basically, the model needs to have the explicit tracking of how many rounds have already been accomplished, right? So in both cases, standard VOMs just easily lose track of the progress in the sequence. So we see that current VOMs are still lack of good embodied planning, which is quite essential for the tracking history over long horizons. And next I will introduce some of our work to address these problems. So first, to address the first issue, the space blindness, I'm going to introduce our work called 3D Aware Region Prompted Vision Language Model. Basically, the core idea here is more like a representation play. So with this representation play, we allow the model to spatially understand the exact entities. And it can also help the model to scale up to the better 3D understanding by leveraging massive amount of web scale to the priors. Yeah, so before jumping into the detail, I'll go through some related work. So to enhance spatial understanding, there are a lot of prior works that try to inject 3D positional embeddings or use features from 3D foundation models as an extra input to the VLM or use it as a supervisory signal. And these approaches all show that 3D cubes are useful, but they usually just treat the 3D information as an add-on. So because they aren't unified, either in the form of architecture or the trimming pipeline, they kind of create a disconnect between single view images and multi-view videos. So as a result, they just lose the powerful web scale to the priors when trying to learn 3D reasoning. And on the other side, we also see a linguistic limitation when relying purely on text tokens. So the example here shows that the chair is to the right of the fireplace. So if a prompt or caption mentioned this, it basically would spread the attention all across the identical chairs in the room. So I call this an attention smearing problem. So it kind of creates massive visual ambiguity. And in complex environments like real world, sometimes text alone isn't just enough to resolve these references, right? So we need some sort of spatial region tokens to directly anchor the model's understanding. So our solution to the first problem is the first problem is the non-unified problem. So we propose a unified architecture that handles both single view and multi-view inputs in the same way. So essentially, whether it's a single view image or a multi-view captured video, the input always consists of RGB and the 3D spatial representation and also the region mask. And for multi-view data, the region mask can either be a 2D annotated box or 3D bounding box projected back to the 2D regions. So to make the whole architecture more unified as possible, we project the single view depth into the exact same 3D space as the multi-view point maps. So everything now gets normalized into a canonicalized world coordinate system. So in that way, we keep the architecture unified, which means the model can hold on those strong 2D web priors while still learning good 3D reasoning. And to handle like high resolution data more efficiently, we use dynamic tiling for single view inputs, and we do frame sampling for the multi-view videos. And actually, this is just more than efficiency. So if we think of the multi-view video frames after sampling, it's a kind of analogous to the localized patches of a single high resolution image. Then basically, we're just treating both inputs as a collection of subregions. So in that way, we sort of make the architecture more unified because the single and multi-view are just consistent pathways. And for spatial cues, following like some of the prior work, we also encode the 3D position map using a standard sign function combined with a lightweight learnable MLP. And basically, we just add these 3DP directly to the visual tokens, which will give the model explicit geometric cues and keep the architecture overhead pretty minimal. So this is actually quite efficient because in that way, we don't use any like heavy encoder like cross-view transformers, which is usually using like 3D foundation models, but just an MLP. And the good thing is that we can also take either ground truth point clouds or pseudo-labeled points from like master or VGGT predictions. So with all the things I mentioned above, this brings together the end of the architecture, where region prompts now become a 3D aware representation for spatial reasoning. So as you can see from the diagram, we can just fed these region tokens directly into the LLM context and then make it do VQA. Yeah. And with these grounded tokens, we can exactly make the model to see like which entities we're referring to. And talking of the training pipeline, our pipeline consists of two stages. So basically, the first stage is a 2D single view pre-training. And then the second stage is 3D multi-view fine-tuning. And the important part of this idea is that we bake the single view training right from the start, not just in the SFT stage, but right from projector initialization and then do pre-training and then the SFT. So basically, it's kind of first time a VOM has been exposed to this volume of depth data from the ground up. So now that we've looked at the training pipeline, let's look at how it actually performs. So before looking at the 3D performance, a natural question is that does forcing this single view depth pre-training hurt the general 2D capabilities? And luckily, looking at these 2D results, the performance are holding quite steadily. Some fluctuations, but all around like 1%. And things get a bit interesting when we look at like 2D benchmarks that needs spatial reasoning. And based on the results, we found that injecting that data clearly helps. So finally, moving to the multi-view benchmark, which are the benchmarks that we care the most, right? Because we're working on like 3D multi-view problems. So we see that our method consistently outperforms like prior works that use points injection or 3D feature fusions. And we also evaluate on a new benchmark called SR3D Bench. Basically, it's a new benchmark we create because there are no video spatial benchmark that includes the annotated region. So basically, we build a data set really similar to VSI Bench, but with optional region annotations inside. Yeah, and comparing our method with some baselines plus SOM, set of marks, we see strong improvements. Basically, set of marks works pretty well for single view images, but for multi-view, it kind of just perform poorly because it's hard to track different annotations across multi-view cameras. So finally, let's look at the ablation study. We find that adding the 3D spatial position encoding alone without the web scale pre-training doesn't really boost the performance much. So this shows that simply injecting the geometric isn't enough. We need to expose the model to massive amount of the data so it can actually learn how to connect the 3D cues from single view to multi-view. So to show some qualitative results, we took a video from YouTube and then do a master to obtain the 3D point cloud and then do like zero-shot inference on our model. And here we show some examples covering both single view and multi-view and with and without the region inputs. Yeah, so maybe just zooming into a specific sample, the query asks like among these multiple pillows, which pillow is closest to the refrigerator? And this is quite challenging because some pillow looks nearly identical. So it's kind of hard to distinguish them using just text. Yeah, and from the last work I just introduced, SR3D shows that 3D aware tokens are quite incredibly powerful for spatial reasoning, but it has a problem. So basically, it relies on a major assumption that someone has already provided those regions prompts, right? So in real world scenarios, we don't have pre-annotated box handed to either us or the robots. So to truly solve the spatial blindness, a model can just reason about the given regions. It needs to be able to actively ground and detect the objects in 3D space. So this brings us to our next project, grounded 3D aware spatial vision language modeling. So basically, we will introduce a visual COT method to like automatically self-ground the object of interest and then do the reasoning on it. The model architecture part is mostly like initialized from the SR3D, the previous work I just introduced. We enriched the visual tokens with both 2D and 3D positional encodings. So it has good spatial understanding. And we also use the same region prompt design so that it can encode the image region as tokens. So to really enable the self-grounded reasoning process, we introduce a method called streaming region insertion loop. So basically, during each step of the model, it predicts 2D regions for the entities that it is about to discuss. And then with the region extractor, we can extract the region embedding and then re-inject it as a token in a streaming way. And the third step is to let the large language model to continue reason toward the task output. So basically, if it is a 3D detection or grounding task, then the LLM should finally output like a 9-dimensional vector, including the 3D box center, scale, and rotation. And again, this architecture is pretty efficient because basically we only extract the areas from the already encoded image features from the clip encoder. So no additional encoding. We just pass them through a lightweight MLP. And also for each region, it's just represented by one token. So it is pretty efficient. The cost is around 0.01 seconds. And basically, it's faster than the Q13 VO series because of the dynamic tiling techniques. So because of this like unified framework design, it is pretty versatile and can accommodate different modes. So the first one is a general spatial QA. Basically, it's a standard mode in like spatial understanding. You just ask some general global question, and then the model just first ground the mentioned entity, and then re-inject the entity region, and then do the answer. And the second one is a region prompted 3D detection. So basically, if there is pre-annotated region, like given by a human or other system, the model can do like sort of 3D reconstruction, reconstruct the 3D box given the region. And also the classic object detection setting, basically just input the raw image and ask the model to detect all the objects that it found and then predict the 3D boxes of all of them. And we can also do the spatial VQA with region of interest and 3D grounding, pretty similar to 3D detection, just 3D detect 3D regions, but given some spatial referring. And the last one is you can do a metric space coordinate prediction with point of interest. Like we just give any point and then ask what is the coordinate of this point. So the results show that compared with Kun 3VL, GR3D is more accurate in both indoor and outdoor settings. But compared with specialist 3D detection models like Detect Anything 3D or CubeRCN, it performs better in indoor scenes, but still falls a little bit behind on outdoor scenes. And we also show that it can like generalize to in the wild samples, like some robotic use case or indoor and outdoor, also some warehouse scenarios. Yeah. And we also show better spatial reasoning, which is especially clear on the blink depth benchmark. So I show a sample here in the left side. So with spatial COT, the model achieves 94%, which is very close to the human performance bar. And to the finding part, we found that two factors contribute most to the 3D detection performance. The first one is to detect in 2D first and then leap to 3D. Yeah, it's kind of like a basic concept in computer vision, right? But in VLM, we found it like, again, very useful. We found that in both indoor and outdoor, it misses fewer objects and can reconstruct the 3D bounding box with a stronger geometric prior. And the second thing is that pre-training on 2D spatial tasks before the 3D fine-tuning. And this is useful because we found that the outdoor samples are quite few in our like training samples. So given the 2D outdoor data, the model can perform better. We also find that the point map reconstructions are really helpful for 3D detection. So if we scale up the point map data, we found that the AP score just keep going up. Yeah. Okay, so I've talked about some our effort among like how to improve the spatial understanding part, and now I'll talk about like the how to mitigate the problem of plane blindness. Yeah. So basically, this is our the third project I introduced. It's called long horizon manipulation via trace condition VOA planning. Yeah. So to understand the problem, let's look at two things. So first, many robot manipulation policies are already performing pretty well on these atomic skills, like grasping, opening, and placing using the imitation learning, using either like transformer architectures or diffusion policies. But there's still a big gap toward like really long horizon tasks. So they are still very hard because of a lot of reasons, like the model needs to know the subtask dependencies. The model doesn't know about the progress right now. And also errors could compound during like the model during the actions, right? So sometimes just small mistake just ruins the whole task. So there are two streams of related work I'm going to introduce, and they have kind of like opposite problems. So on the left, we have the trajectory condition models like Momo egg and hamsters. And these are really great models because they provide a dense geometric constraints by drawing the 2D trajectories or key point directly onto the scene. So, but they are usually like monotonic, and so they do not have really high level planning. They basically operate purely on the short horizons and have no semantic mechanism to track the progress or reason about what to do next. And on the right side, we have the exact opposite paradigm. So there are like really good work, like from Google DeepMind, like using symbolic tags or code planners. We see inner monologue, code as policies, and also like POMI. These are really good at high-level subtask planning, sometimes using LLM and some use VLM, and they can also like track the task between stages. But the problem is that they are usually like space blind. Their tag sub-goals doesn't really offer any local geometric grounding. So which leaves the low-level policy to quite struggle with compounding execution errors. So this inspired us to propose this local manip paper, which try to combine both of the worlds. Basically, we want to bring high-level planning and geometric grounding together in a single framework. So here is the brief framework overview of our trace condition VOA planning. So basically, the system has a high-level VOM that will track what is already done, what remains to be done, and guide the low-level execution using some visual traces. So to break it down like quickly, so given an observation image and a task instruction, the task manager, which is a lightweight VOM, will predict the task progress. And also the next subtask that the low-level policy should execute, and also the spatial visual trace indicating that what interaction trajectory the robot arm should interact with the scene. So, and then the low-level executor, which can be like any off-the-shelf policies like the GRUT or pi 0, 0.5 or anything. Yeah, just need a little bit fine tuning. And this low-level executor basically just taking the subtask and also the trajectory and then perform the action. And the whole system operates in the closed loop. So after like executing each actions, we just fed the new observation back to the VLM manager. And then the manager just update the task progress, like what is done, what is still working on, and generate the next subtask and trace to the low-level VLA. The good thing with that is that so we can basically customize the scheduling. So like this kind of two-level framework, we can make the high-level VLM work on a lower frequency and make the low-level executor VLA work on a really high frequency since it's like a smaller. So and with that, we can allow the system to run periodically on the high-level reasoning, but the low-level part are just fast and robust. So next is our like a receding horizon data generation engine, which we designed this to automatically collect data and scale up our training data for training the high-level task manager. Yeah, so basically given some raw manipulation videos, we use a bunch of different vision language foundation models to perform some data processing like frame grounding, object detection, captioning. And so with that, we can automatically identify some interaction actions. Like we can get the atomic subtask given a video, and we get the start and end frame of each subtask. And also we get the any vector position for each of the frame, which I highlighted in the like the white box here. And we also get the target item position as well as the grasshopper item position, which will be used to generate some error correction data by like swapping the instructions with some other samples. Yeah. And the key highlight here is that the pipeline is pretty versatile. So it can be applied to any of the shelf data sets across different embodiments, including like human hand videos. So let's quickly look at a concrete sample generated by the data engine. So here you see a raw video being automatically broken down into like different subtasks and what to do next, and also the trajectories. Yeah, and eventually we'll predict that the whole task is being like completed, so it should be stopped. And also it can synthesize the errors recovery data I just mentioned by giving the model to a trajectory that recovers from the wrong objects. So moving to the results, our framework achieved leading performance on planning and reasoning benchmarks. The high-level task manager is actually just a 4V model, and it outperforms the proprietary models, including open source VLMs and also like some Gemini models. And we tested on like different benchmarks, Robot VQA, Eagle Plan, Embody Bench. And so basically it's pretty effective on long horizon reasoning and planning and progress tracking. And next, we also see pretty strong cross-embodiment trajectory prediction results. So basically, it can handle different robot arms, like we see Frankai and UR5 here, and also different any vectors. We got grippers and dex hands. And also, it can handle different camera viewpoints. So either you use an egocentric video or you use a third-person view, it works pretty well. So finally, let's look at our real-world rollout results on two tasks. So the left task is to find all the hidden eggs in the cabinet and drawers and put them into the sink. And the second task is to like sort the items, putting all fruits and vegetables into the black bowl and everything else into the container. So both tasks are quite challenging because they require multi-step planning, and we need constant progress tracking, and it needs to be robust over a long period of time. Yeah, basically that's all. And to conclude, there are three main takeaways from our work. So first, to overcome the space blindness, I think a good representation design can help the models to really pinpoint to the exact physical entities, and a good representation can also help the model to scale up better. Yeah. And second, to mitigate the plan blindness problem, we should do more grounding and planning, like a receding horizon visual trace thing to make the model more robust on long horizon planning. And third, grounding is the key interface that can connect high-level reasoning with physical actions. Yeah, basically that's all. And thank you for coming here today.